Hey everyone, this is the Lifesavers with the Light F Bulb project. Our team consists of Ahmad, Slav, and David. For our project, we decided to make a safety lamp that is automated and light adjusting. This lamp will provide light as a regular lamp, but also act as a household safety device. It detects the current room lighting and adjusts the bulb's brightness according to a light level measured. As seen on screen, we each had a specific role. In addition to our roles, we all worked together on documentation, data logging, finite state machine, code, and the slides and lab report. Here we have the finite state machine. The first state prepares for data capture. Next, we measure the light level with the light sensor. Based on this measurement, the light is changed to a corresponding brightness. After this, the next state measures this temperature. Based on this temperature measurement, if it is more than 80 degrees Fahrenheit, a sound is played and the corresponding LED turns on. However, if the measured temperature is less than 80 degrees, just the corresponding LED is turned on. Finally, the data is logged and the cycle continues to repeat. Here we have the block diagram. To the right, we have the input from the temperature and light sensors, which are connected to the STM32 board. Next, to the left, we have the output going to the bulb, LEDs, and alarm. We also have communication with the Raspberry Pi to log the data we collect.
Light bulb portion of our project. For my portion, I was responsible with creating a smart light bulb that is enabled depending on the surrounding light. So to build this portion of the project, I use an STM32 board for the LED automation, and I use a Raspberry Pi for the data logging. As pictured here, I hooked up a photoresistor and a capacitor to the breadboard, as well as the power ground to the Raspberry Pi pins. This would later allow my script to capture the photoresistor readings and then direct them to a log on the Raspberry Pi. Then as we see pictured over to the left, I use the STM32 board for adjusting the light bulb output. The photoresistor would be connected to an input pin, while the LED would be connected to an output pin on the STM32. So pictured here is a Python script which automates the data logging process and sends the LDR value readings into a .txt file organized by the date, time, and value. The script is set to a new log and is set to log a new entry every 30 seconds. And this would later allow us to better understand our light usage and potentially adjust accordingly. The following slide contains a short code segment for the general logic of the LED automation on the STM32. For the testing purposes, the code is currently placed in the main while loop, but once incorporated with the rest of the project, it would be a case in the FSM. The code reads the surrounding light from the photoresistor. If it detects a reset, or in other words, no light, it will switch the LED on. However, once the photoresistor does read light, it will automatically switch the LED off, accomplishing our light adjusting automation we set out for in the project. So a screenshot of the .txt file generated is pictured here. When the room lighting is dark, we see a higher LDR value and the LED light up. And we see the opposite when light is present, evidenced by the lower LDR value readings and LED automatically switching off. For the purposes of the demo, all the test cases were recorded in a controlled environment. So in other words, I manipulated light presence every couple of minutes. Rather than looking at the raw data values, I've compiled them into a chart. On the y-axis, we have the photoresistor values, and on the x-axis, we have the time. So in our first segment over here, this would be the natural window light, and it would be recorded across around 6:40 p.m. Initially, I saw an unreliable reading as the sensor adjusted the room lighting, so for the purposes of the graph, I excluded the first 4 or so values, and after a couple of minutes, we start to see a consistent recording form. At this point, the LED is automatically switched on. In the second test case over here, this is with the room light on. We see a steep drop-off in the LDR readings, and at this point, the LED automatically switches off. In the third test case, I've attempted to block off all artificial and natural light, and we see a jump in the LDR value readings, and the LED is on. In the last test case over here, I've attempted to direct as much light as possible onto the sensor, and we see our lower values recorded. So here is a video of the board running the code. Take note of the LED as it switches off with the light on, and we see a lower values being read over here. As the LED, as the light is switched off, we see it LED power back on, and again, and that concludes this portion.
In the group project, I'm going to be discussing the temperature sensor and the buzzer. So the temperature sensor, or thermistor in our case, is a sensor used to measure the temperature of a given environment. As we know, resistors all change temperature when using any live circuit. They'll heat up, etc. So a thermistor provides a large change in resistance value when there's a change in temperature, which will provide a sensitive and accurate reading. Thermistors are very common. You'll find them in fire alarms, microwaves, etc. So there's 2 types of thermistors. So one's negative temperature coefficient, NTC, which we'll be using. The other one's a positive temperature coefficient. So in our case, it pretty much as the thermistor temperature increases, the resistance of it will decrease. Using this characteristic, I'll kind of discuss about how we use it a little bit later. So in short, in our case, the temperature sensor will be used to measure the temperature of a given environment, and will output buzzing noise depending on temperature results. So if the temperature is greater than 80 degrees Fahrenheit, a red LED will be displayed, and a thermometer will be notified with the buzzing sound. Otherwise, a blue LED is flashed on. Okay, so here's a picture of the circuit. I discussed about it a little bit more in the YouTube video. The YouTube link's right there, but for now, pretty much, I'm going to be using a comparator. And in this comparator, it's going to compare these two input voltages. The two sets of input voltages are pretty much voltage dividers between two 10K ohm resistors, and the other set is going to be a 110K ohm resistor and a thermistor. So when the thermistor heats up, the resistance will decrease, and obviously the comparator will notice this change. And once it notices this change in the thermistor's temperature increasing, and as we know, as the temperature increases, the resistance of the thermistor will decrease. So the comparator will obviously notice this change and will notify the user. So the output of that will be the buzzing noise. The output will go to a that's where we use the NPN transistor, which is pretty much amplifies the current, allowing enough current to flow through the buzzer, and the buzzer will obviously buzz and notify the user that the thermistor is getting too hot, it's a little too hot in the room, etc.
Hello, my name is Slav, and my main part for the lab was to set up and write a code for the LED lights to light up depending on the temperature. The equipment I used included two LED lights of two different colors, two 330 ohm resistors, a kilo ohm resistor, connecting wires, the STM32F767, and of course a breadboard. Here we have a snapshot of the LED light setup I made on the breadboard. I connected it with pins on the STM32. I included my code in the lab report, but this was very similar to the stoplight lab we did for lab number 2. Based on the current temperature measured, a specific LED was supposed to light up. If the temperature was measured less than 80 degrees Fahrenheit, the blue LED lights up. However, if the temperature is higher than 80 degrees Fahrenheit, the red LED lights up. On this slide, I attached the possible outcomes of the LED lights when the program is running. When the lamp is getting the data from the sensors, the LED lights will be like image A with the lights both off. If the data collected provides a temperature higher than 80 degrees Fahrenheit, then the LED will look like image B. The blue will be off and the red will be on. However, if the temperature is lower than 80 degrees Fahrenheit, the LED will look like image C with red off and blue on. In conclusion, we were able to program and make a functional finite state machine on an STM32 board that controls a safety lamp. Here's an image of the light being controlled with a sensor. This was controlled using a light sensor and a temperature sensor to activate a buzzer and a specific LED based on the temperature. Thank you.